Before I get started, I first wanted to thank the organizers for the opportunity to speak here today. It's a real pleasure for me to give a talk at this conference, especially because it's in honor of Greg Lawler. And I think, like many other people here, I first got into this field by reading Greg's book on SLE. So this talk is going to be based on some joint works I've been doing with Scott Sheffield from MIT. And my talk is going to have three parts to it. In the first part, in the introduction, I'm going to remind you of some of the basic random planar map and Liouville quantum gravity background. And then I'll tell you what our main result is. And then in the second and the third parts of the talk, I'm going to tell you about how we prove our main result. And this is going to involve a new characterization of the Brownian map and a construction of a metric on Liouville quantum gravity using a growth process we call QLE. Okay. All right, so just to remind you, a planar map is just a finite graph in the plane so that no two edges cross. And the faces of a planar map are just the connected components of the complements of its edges. And a map is said to be a quadrangulation if it has the property that each face has exactly 4 adjacent edges. And if you look at this picture over here that I've drawn on the left-hand side, you'll see that this really is a quadrangulation. And in this talk, we want to think of quadrangulations as somehow corresponding to metric spaces, where here the notion of distance just comes from the graph distance, the underlying quadrangulation. And we're going to be interested in the measure on random quadrangulations, which is just given by picking them uniformly at random with a given number, let's say n faces. And I'm going to refer to these objects as random planar maps and sometimes abbreviate them by the acronym RPM. All right, so now let me remind you of some of the basic and very important results about the structure of random planar maps with a large number of faces. So first of all, it was shown by Chasing and Schaefer that if you have a planar map with n faces, its typical diameter turns out to be about n to the 1/4. And then it was later shown by Jean-Francois Le Gall that if you take distances and you rescale them by the factor n to the -1/4, then this gives you a tight sequence in the space of metric spaces. So what this means is that you can construct subsequential limits. And it was also shown by Le Gall that every subsequentially limiting metric space has to have dimension 4. And it was shown in two independent works, one of Le Gall and Paulin, and then later by Gregory Miermont, that the subsequential limits are also homeomorphic to the two-dimensional sphere. And then finally, all of these works culminated with these two very big and independent works, one by Le Gall and one by Gregory Miermont, where they showed that it's not necessary to pass along a subsequence in this construction. You really do have a true limit, and this is what the Brownian map is. And this picture here on the left-hand side is just to give you a sense of what a large quadrangulation looks like. This has 25,000 faces, and it was generated by Jean-Francois Macron. Now, one of the things that I want to emphasize is that the Brownian map is not just a metric space. It also has a very natural measure on it, so it's a metric measure space. And in terms of discrete approximations, where does this measure come from? Well, it's just the scaling limit of the measure on your random planar map, which assigns unit mass for each vertex and then normalized so that you get a non-trivial limit. So the Brownian map is a metric space, but it also, very importantly, it has a measure. Okay, so that's the very quick review of random planar maps. Now let me remind you of the definition of Liouville quantum gravity. So the starting point is that you have a planar domain, and then on your domain, you have an instance of the Gaussian free field. Now, I know that we heard a lot about the Gaussian free field in the previous two talks, but let me just quickly run through the definition. So the Gaussian free field on D is just a Gaussian process indexed by points in D, where the covariance function is given by the Green's function for the Laplacian on D. And as everybody knows, the Green's function has a logarithmic blow-up along the diagonal, and so what this means is that the Gaussian free field has infinite variance at points, and so it doesn't make sense as a function, but rather as a distribution. All right, and what is Liouville quantum gravity? So Liouville quantum gravity is the object that you get when you take the Euclidean metric and you perturb it by the factor e to the gamma h, where h is a Gaussian free field and gamma is between 0 and 2. And the reason that I put here the words random surface and Riemannian metric in quotes is that, of course, this expression doesn't make literal sense because h is a distribution, and what does it mean to exponentiate a distribution in this way? And previously, this object had only been made sense of as an area measure. So the operation that you can perform is that you can calculate areas of regions. And the way that this was done is by taking this Gaussian free field here, approximating it by something nice, and then showing that the associated measures have a limit. And this appears in a number of places, for example, in the work of Kahan and also Duplantier and Sheffield. All right, and so what is the structure that you get with Liouville quantum gravity? Well, you have two parts to it. So number one, you have a conformal structure. So you know how to compute angles, you know what harmonic functions are, etc. And then you also have this area measure. And in contrast, the Brownian map, its structure also consists of two parts. So you have a metric structure and an area measure. And what this talk is about it's about endowing each of these objects with the other structure and then showing that they are the same, they're equivalent. Okay. Okay, so again, the Brownian map, this is just an abstract metric measure space, which is homeomorphic to the sphere. And as Stefan was saying in his talk, it's not clear a priori what the right way is to embed the Brownian map into the sphere. But it's been believed for a long time that there should be a natural embedding of the Brownian map into the sphere, so that when you embed it in this way, what you get is described by a form of Liouville quantum gravity where this parameter gamma equals the square root of 8/3 comes up. And also, as Stefan mentioned, kind of the natural approach to construct this embedding is the discrete approach. And what you would do here is you would take a uniformly random planar map like this one, and then you would embed it into the sphere conformally in some way. So for example, you could do this with circle packing, Riemann uniformization, or whatever. And then you would try to show that when you take a limit as n goes to infinity, what you get on the right-hand side converges to a form of Liouville quantum gravity with this value of gamma. Gamma is equal to the square root of 8/3. So this is kind of one approach that you could take, but I want to emphasize that today we're going to be describing a different approach to this problem, which won't involve any discrete approximation. Okay. All right, so now let me tell you what the main result is. So the main result is that if you have an instance of the Brownian map, so remember this is a metric space together with this measure mu, then there exists a map which is a homeomorphism, and it takes the Brownian map into the sphere such that the push forward of this measure by the embedding actually is a form of Liouville quantum gravity. When gamma is the square root of 8/3, it's the so-called Liouville quantum gravity sphere. And not only is this map a homeomorphism, but it turns out to be Holder continuous in both directions. Okay. And moreover, the embedding is actually a deterministic function of the Brownian map. So what this means is if you just see the Brownian map, then you know how to embed it. It's really a measurable function. So this says that the Brownian map actually determines its conformal structure uniquely in this way. It's also true that if you just observe the Liouville quantum gravity surface, then both the Brownian map structure and its embedding are also deterministic functions of it. So in other words, Liouville quantum gravity determines its metric space structure in a unique way. Okay. And therefore, both of these objects are equivalent to each other. Again, in the sense that if you observe one, you can recover all of the structure of the other one in a unique way. Okay, let me make a few comments about this theorem statement. So just to emphasize one more time, this is going to be purely a continuum proof. There won't be any discrete approximations. Secondly, the way that the proof is going to go is it's not by somehow constructing an embedding on the Brownian map side into Liouville quantum gravity. Rather, the first step is to try to build a metric space structure on these Liouville quantum gravity surfaces using this growth process QLE, which I'll tell you about a little bit later. And then after you've constructed this metric space structure, you show that it's isometric to the Brownian map by showing that it satisfies a certain set of axioms which turn out to single out the Brownian map among all metric spaces. And at this point, what you know is that the Brownian map structure is sitting inside of Liouville quantum gravity, and the Brownian map structure is actually a deterministic function of it, and there's an extra argument that you need to show that if you just see the Brownian map, then you can uniquely recover what the Liouville quantum gravity sphere must have been. And one final comment, and it's that all of this work in Liouville quantum gravity takes place on a very special surface, which is this Liouville quantum gravity sphere. However, once you know how to construct the measure or the metric in this setting, by absolute continuity, you can actually construct a metric on any Liouville quantum gravity surface with this parameter here, the square root of 8/3. So you get the metric in all possible settings. Okay, so this is the main result. What I want to do now is tell you first about the axiomatic characterization of the Brownian map, and then I'll switch over to QLE. Okay, so let me begin by reminding you of the construction of the Brownian map. So the way that it goes is you first sample a Brownian excursion, let's say a standard Brownian excursion on this interval, and this is just the graph of this function over here. And as I'm sure everybody here knows, if you take a Brownian excursion and you glue it together by identifying points on the graph, if they can be reached by a chord which lies below the graph, then what you get is a continuum random tree. Okay, and the second step is once you've sampled your Brownian excursion and you've fixed it, so you've conditioned on it, you sample a Gaussian process, y, where the covariance function for this Gaussian process at given times, let's say a and b, is just going to be the minimum value that the Brownian excursion takes in the interval from a to b. And the way that you should think of this is that this process y is just defining for you a Brownian type process on the tree, where if you start from its root and you run along one of the branches, it's just evolving as a Brownian motion. And whenever the tree branches, the Brownian motions start to evolve independently. And on the top here, I've drawn a graph of c minus y. So c here is just a large constant so that these two graphs are disjoint from each other. And then you can take this graph up here, and you can also glue it together. And the way that you do that is the same as we did below. So you just say that points are the same if they can be reached by one of these green chords, and you get another tree. And this is going to be the geodesic tree in the Brownian map. And the way that you glue these two trees together is that you just draw in these vertical chords here, and you say that 2 points are equivalent if they lie on the same vertical chord. And this induces a gluing over here on this side with these two trees. So far, this just defines a topological structure. Where does the metric come from? Well, the metric just comes from taking the geodesic tree up here and then quotienting out by this equivalence relation, this gluing. And finally, where does the measure come from? The measure is just the projection of Lebesgue measure on the interval from 0 to 1 over to the quotient space. Okay, so this is the Brownian map, and what I want to do now is try to describe some properties that the Brownian map has which turn out to characterize it among all metric spaces. And as is often the case with these types of continuous models, it can be very difficult to see just from this type of definition, what properties it should have. How would you characterize it? And so the usual game that one plays is you look at discrete models, which converge to, say, the Brownian map. You see what properties they have, and then you try to show that the continuous model also has the same properties. Okay, and so with that in mind, I want to show you a picture now. So this is a random triangulation. And in this picture, I have 2 points. I have x and y. And I want you to think of these 2 points as having been chosen uniformly at random from the uniform measure on the vertices in the map. And then what I can start to do is from this point x, I can start to grow a metric ball. So this is the metric ball, for example, of radius 1, 2, 3, 4, etc. And actually, at radius 5 here, I've drawn not a metric ball, but a filled metric ball, because I've included in the orange region these vertices here, which actually have distance larger than 5 from x. And so the way that this is done is you just take the set of vertices which have been disconnected from y by the boundary of the metric ball. You just add those to your cluster. And because this map is chosen uniformly at random, it's kind of obvious that if you condition on the boundary length of this metric ball, then the inside and the outside of it are going to be independent. And so you could resample them one at a time. So this is one property that is clear on the random planar map side. Here's another one. So what I've done now is from each point on the boundary of this cluster, I've drawn a geodesic from that point back to the root of the map, or sorry, of the center of the metric ball. And, you know, of course, there can be many geodesics from any one point, so you need a way to make these canonical. And the way that this is done is that these are all leftmost geodesics back to the center of the ball. And, okay, once you've drawn these geodesics, this has the effect of taking the ball and slicing it into a bunch of pieces. So here in this picture, there's 1, 2, 3, 4, 5 geodesic slices. And also because this map is chosen uniformly at random, it turns out that you can also resample these geodesic slices one at a time with respect to some conditional law. Okay, so these are properties that you obviously have on the discrete side. And so now what is the theorem statement about what's true in the continuum? Well, the theorem statement says that the Brownian map is the unique measure on doubly marked geodesic metric spheres, which also come with a measure, which has the following 3 properties. So first of all, you can resample the 2 marked points independently from the measure mu once you've fixed everything else. So these points are just uniformly random. And secondly, if you fix a deterministic value of r, and you condition on the event that the distance between these 2 points is at least r, then it's true with either of these 2 values of s. So s can either be equal to r, or the distance between x and y minus r, that you have some way of making sense of the boundary length of your metric ball, such that the inside and the outside of the ball are independent given this boundary length. Okay? So you have your metric ball in the Brownian map. Actually, this is a filled metric ball. Maybe it looks something like that. And this first assumption says that you have some way of assigning a boundary length to the boundary of this ball so that the inside and the outside are going to be conditionally independent given this boundary length. And the second property is that you actually have a little bit more structure here. So not only do you have a notion of total boundary length, but you have a measure on the boundary which allows you to assign boundary lengths to subsets. And what the statement is here is it's just the analog of the slice independence, and it says that if you pick a uniform point, let's say on the boundary of your filled metric ball, and then once you've done that, you lay out a total of n points like this. Sorry. So you have your n points, and then you slice your metric ball with geodesics. Then just like in the discrete case, the behavior of the surface inside of these geodesic slices is conditionally independent once you've fixed the total boundary length of the metric ball. And moreover, the law of each of these slices, these just depend on the length of the part of the metric ball which forms its boundary, which is L of s over n, in a scale invariant way. And so the theorem statement says that if you satisfy these properties, then you have to be the Brownian map. Now, one thing I want to just remark on is that in order to make this type of theorem precise, one thing that you have to do is you have to specify what sigma algebras you're going to use for these random variables. And this actually leads to some kind of interesting and fun measurability questions. So one measurability question you might ask about is it true that a metric space, which is geodesic and homomorphic to the sphere, so this is an event that you can define in the Gromov-Hausdorff topology, and you can ask the question whether or not this event is measurable with respect to the Borel sigma algebra in the Gromov-Hausdorff topology. And similarly, you can ask whether or not the different functions that we've just defined here are measurable functions with respect to, say, this topology. And these are things that you have to be able to answer in order to make something like this precise. And these are actually fun exercises to think about. Okay, so this is the theorem statement. Now, what I want to do is say a little bit about how you see that this is true.
I assume the answer is yes to that?
Yes, yes, that's right. That one's yes. Right. I hope so. All right. Okay. Yeah. So going back to the Brownian map construction, so the usual way that you construct the Brownian map, like I described earlier, is in a depth-first manner. And what I mean by this is that, if you follow the preferential direction of these two functions, x and y, from left to right, and you think about what's going on the Brownian map side, well, what you're doing is you're just tracing the outer boundary of this tree. And so you're going kind of as far along as you can along the geodesic tree before traveling left. And one of the important ingredients in the theorem is not to give a depth-first construction of the Brownian map, but rather a breadth-first description of the Brownian map. And in order to do this, you have to be able to do a couple of different things. So first of all, you have to make sense of this boundary length measure for metric ball boundaries. So somehow you have to think of a way to define this. And secondly, it's also important to construct the law of what should be a Brownian disk, and it should describe what the unexplored region is when you perform metric exploration on the Brownian map. And this part of our work actually overlaps with a number of other works which are currently in progress. So for example, Nicola Kurian gave a talk about a work that he has ongoing with Jean Bertoine and Igor Krochemsky, which also contains in it a breadth-first construction of the Brownian map. And then there's also another ongoing work with Celine Abraham and Jean-Francois Le Gall, where they construct and understand these Brownian disk measures. And lastly, we heard another talk in the last conference by Gregory Mirmont, which is on a joint work with Jeremy Bettinelli, where they're also constructing these Brownian disk measures, showing that they're the scaling limits of certain types of random planar maps, and doing lots of more refined things that we do in our work. Okay, so I don't want to say much more about the breadth-first construction of the Brownian map. Rather, what I want to do is explain to you how you can start to immediately see the Brownian map structure once you make the assumption of slice independence that I mentioned earlier. Okay? So it's going to turn out that this assumption of slice independence, together with scale invariance, is going to restrict the possible laws of things that you can get to a one-parameter family. And here's how this works. So what I want you to imagine is that this shape here, this is a filled metric ball in the Brownian map, and I've picked a uniformly random point on its boundary, and this blue path here is just a geodesic back to the center of the ball, to the root. Okay, and now what I've done is I've drawn this red arc here, which is 1 unit of boundary length in the counterclockwise direction. And then I've drawn a second geodesic from this point also back to the root. Okay, and what we want to look at is the law of what I'm calling A, and what A measures is how far you have to travel back along these two geodesics before they merge. Okay, so A is the merging time of these geodesics. So the first thing that you could imagine doing is you could imagine subdividing this arc into two, so now that this has a length a half, and this has length a half. Okay. So now we have 3 geodesics, and what you get is that the merging time, A1, for these 2 geodesics, is going to be independent of the merging time A2 for these 2 geodesics. So they're going to be independent. And not only are they independent, the merging time of the leftmost and the rightmost geodesic is just the maximum of the two merging times. And the hypothesis of scale invariance tells us that each of the AIs is given by taking the, in distribution, is given by taking A and scaling it by some factor. Okay? So this already starts to restrict the law of A. And you can imagine just iterating this a bit more. So here in this picture, I've done the same thing, except for instead of having 3 geodesics back to the root, I now have 5. So I've subdivided my unit length interval into 4 pieces. And each of these boundary lengths are have equal length 1/4. Okay? And again, the successive merging times are going to be independent by the assumption of slice independence. The merging time of the leftmost and rightmost geodesic is just given by the maximum of the merging times. And the assumption of scale invariance tells you that the law of the ith merging time is equal in distribution to the total merging time scaled by this factor here. And as I'll explain in just a moment, if you continue to iterate this procedure, this will actually determine the law of A up to a single parameter. Okay. And once you know the law of A, this actually determines the entire law of the geodesic tree back from the boundary of this ball to the root. Again, just from slice independence and the form of the law of A. And if you vary the radius of your ball and use inside-outside independence, this actually determines the entire law of the whole geodesic tree in your metric space. Okay? And so the entire thing is just determined by the law of this A here. Okay, so now let me go back to figuring out what the law of A is. So if we do what we did before, not with, say, 4 geodesics, but you do it with 2 to the n geodesics, then what you know is you can write A as the maximum of 2 to the n AIs, where each of these guys are IID, and they're equal in distribution to A, but scaled by the factor 2 to the minus n beta. And it's just a very easy exercise to see that the cumulative distribution function for A has to take the form something to the r to the minus 1 over beta power. So it's a little exercise that you can do. Now, on the Brownian map side, you can also do a calculation. And there, it turns out that this exactly holds, but the value of beta is given by 1/2. And for people who are experts on the Brownian map, the reason that you see 1/2 there is just due to the fact that if you draw a metric ball and you draw 2 geodesics back to the root like this, and then you ask, how does this boundary length here evolve as you shrink the size of the ball? Well, it turns out that it evolves, this boundary length is evolving as what's called a continuous state branching process with a certain branching mechanism. So it's just u to the 3/2. And for this type of process, you can do a little calculation and see that this is going to give you beta equal to 1/2, because this is just the first time that this process dies out. And so to finish showing that the geodesic tree that you have in your metric space has the same law as the one in the Brownian map, what you need to do is you need to show that the theorem assumptions imply not that there's some beta so that this is true, but you have to pin down the value of beta and try to get it to be 1/2. Okay, now I'm going to say something which is not going to make a lot of sense unless you know what it's supposed to be, just like Wendelin had in his talk. So there's some way of using scale invariance to show that the conditional expectation of the area in a disk, given its boundary length, turns out to be L to the 2 beta plus 1. So there's some way of checking that. And then there's a little Levy process argument that you have to do that shows that, as you explore in the Brownian map one of these Brownian disks, then the conditional expectation of the area can only be a martingale when this value of beta is equal to 1/2. So basically there's a martingale argument which is underlying all of this, which singles out this particular value of beta here. And once you know that the law of the geodesic tree is the same, it's not too much work to finish it off and see that it really is the Brownian map. All right, so that's the Brownian map side of the story. Now let me go to the construction of the metric on the Liouville quantum gravity side. Okay. So let me first give you an overview of what's going to go on here. So what we're going to try to do is we're going to try to construct a metric on square root 8/3 Liouville quantum gravity by making sense of what has to be the scaling limit of first passage percolation on a Liouville quantum gravity surface. And this is a growth process which we call QLE, and it has these parameters 8/3 0 here. And the reason that I keep including these parameters is that this is actually a member of a whole family of growth processes, which we call QLE gamma squared eta, which we conjecture to describe the scaling limits of things like diffusion limited aggregation and the dielectric breakdown model on Liouville quantum gravity surfaces. Okay, and it's not going to be clear from the construction that this actually defines a metric on the Liouville quantum gravity surface. This is going to require some extra work, and it's going to come from kind of building at a very basic level from the reversibility of SLE6 and a very clever argument which was developed by Scott together with Hao Wu and Sam Watson for checking that things define metric spaces. Okay, so that's the plan. So let me begin by just giving you a little reminder of what first passage percolation is. So for first passage percolation, you imagine that you have a graph like this one, and then what you do is you decorate your graph with IID exponential 1 edge weights. So maybe you get something that looks like that. And what you want to understand in first passage percolation is how the metric, the graph metric, behaves when you perturb it in this particular way. Okay, and very roughly, if your graph somehow has enough isotropy, so it doesn't have really any preferential directions, then what you would expect is that at very large scales, when you perturb the metric with these types of edge weights, at large scales it's going to behave just like the original underlying graph metric. And and so there are two formulations of first passage percolation. There's the Eden growth model, introduced in 1961, and also the version introduced by Hammersley and Welsh in 1965, which is what I just described to you. The Eden growth model, what it is it's just a Markovian way of growing a metric ball in first passage percolation step by step without first sampling all of these edge weights. And this is actually the perspective that we want to take, and what I want to do now is explain why this is a good idea from the discrete perspective. Okay, so what I want you to imagine here is that we have a large triangulation out here, and what I'm going to do is perform a version of first passage percolation starting from this vertex x. And what I've done here is I've actually included all of the triangles in the graph which are adjacent to x. And the way that it works is that you just look at each of the edges on the boundary of your cluster, you pick one at random, and then you just explore the triangle which is opposite of that edge. And so maybe you get that triangle. And then you do it again. You look at the cluster, you pick an edge uniformly at random, and then you add the opposing triangle. Okay? And you keep doing it. Maybe you get something that looks like that, etc. This is the Eden growth model formulation of first passage percolation. And the very important observation is that because of the way that this growth process is defined, you understand at every step exactly what the conditional law of the unexplored region out here looks like. And in fact, in all of the unexplored components. And it's just going to be a function of the boundary lengths of the corresponding components. So this is very important, and this will come back just a little bit later. So this exploration respects in a good way the Markovian structure of this map. And the belief is that, because this is a random graph, it should have enough isotropy, doesn't have any preferential directions, so that at large scales, this defines a growth process which looks very, very close to the usual ball with respect to the graph metric. And this belief has now been confirmed in work of Nicolas Carrion and Jean-François Legal. They showed that it really is true that when you do first passage percolation on a random planar map, at large scales, you do recover the underlying graph metric. Okay, so this is one version of first passage percolation. In reality, we're going to use a version which is related to another construction. And so in this second version of first passage percolation, I imagine I have the same setup as before, except for now I'm going to attach pieces to this cluster in a slightly different way than I did when I did in the previous slide. And so the way it works is that I first pick two edges on the boundary of my my cluster, like maybe the top edge here and the bottom edge, and I'm going to color the vertices between these two edges yellow and blue. So this is the blue side over here, and this is the yellow side over here. And then I want to imagine that in the rest of the map, all of the other vertices have been colored either blue or yellow with equal probability a half. And then I'm going to take one of my two edges, and I'm going to draw a little bit of percolation exploration from that edge. And after I finish the first step, I'm going to forget the colors that I had before. I'm going to pick, I'm just going to repeat the process. I'm going to pick two more edges uniformly at random, maybe this one and this one. I color this side yellow, this side blue, and then I add another chunk of percolation exploration. And then again, I forget the colors, pick two more edges, and just keep repeating. Okay? And so this is just like regular first passage percolation, except that each step, I'm not adding individual triangles, I'm adding little chunks of percolation interface. But just like before, this exploration also respects the Markovian structure of the map in the sense that you know the conditional law of the unexplored region, and it's just a function of the boundary length. Okay. And you would also expect that there's some universality in this first passage percolation result that tells you that it does not matter, what the exact shape of the little chunks are that you're adding at each stage. It should still be true at large scales that you are getting something which looks like the metric ball in the original graph. Okay, so this is the motivating discrete idea. So how do you do the same thing in Liouville quantum gravity? Well, what you do is you just replace these percolation exploration chunks with SLE6s. So if we want to grow our cluster here, we imagine we have one of these square root 8/3 Liouville quantum gravity surfaces. We have a point that we want to grow the cluster from. And so what we do is we just draw a little bit of SLE6 starting from that point. And now what we want to do is we want to forget the colors on the left and right sides of this SLE6 or percolation chunk, and then re-randomize, which just corresponds to resampling the location of this tip where we're going from according to boundary length. And then you repeat and draw a little bit more SLE6. And then you just keep doing this, etc. And it's true that just like in the discrete side on random planar maps, we know exactly what the conditional law of each of these holes are given its boundary length. So it's given by some kind of quantum surface. And so finally, what is QLE? QLE is what you get when you take the limit as delta goes to 0. This is the chunk size of this, this growth process. Yep?
So what you call the units of SLE6, how do you do it?
Yeah, so, right, so there are two different natural notions of unit. One natural notion of unit is capacity time, and in the original QLE paper, that's the notion of time that we used. But in the metric construction, the unit that we use is what we call quantum natural time. And what quantum natural time is it is the natural analog of the natural parameterization, but in the setting of Liouville quantum gravity. So it should be just the scaling limit of the number of edges that one of these percolation interfaces requires. So it's a quantum intrinsic notion of time, again, just like the natural parameterization, but on Liouville quantum gravity. Okay, and this is what QLE is. And one way of thinking about what QLE is it's just what you get when you take one of your SLE6 processes and you perform this operation of tip re-randomization, which means you just forget where you were growing infinitesimally often. Okay. And here's a picture of what QLE looks like or at least a simulation I made of QLE. So this is some kind of graph approximation of Liouville quantum gravity. And this picture was generated by doing first passage percolation on this graph approximation. This gives you a sense of what these processes actually look like. Okay. Now, what I want to do is I want to explain the strategy for showing that QLE actually defines a real metric space structure. And again, at this point, all that we know is that we have a candidate for a process which might define a metric space structure, but it's not at all obvious that it really is going to give you a metric. And so how do we do this? Well, as a starting point, what we're going to try to do is not define a metric on every point in our space, but rather just on a countable dense set. Okay? So what you first do is you imagine choosing a sequence, an IID sequence, Zn. So these are IID from the Liouville quantum gravity measure. So you have all these points inside of your Liouville quantum gravity sphere. And these are the Zi. Okay? And once you've sampled your points, what you do is for each point, you imagine having, you sample one of these QLEs growing from it. Okay, so I've just drawn a little bit of the growth process for each one of these points. And the way that these things are coupled together is that once you've fixed, sorry, I guess I called these xi's in the slide. So once you've fixed these points, you sample all of these growth processes conditionally independent given the Gaussian free field. Okay, and so from each point you have something which should be like a metric ball growing from that point. And okay, now if you have any pair of points, like let's say this one is xn and this is xm, what you can do is define what you think is going to be the distance between xn and xm, and what it is you just grow the process which is starting from xn, and you just wait and you see how long it takes for xm to be contained in the boundary of your growth process. And you just call that the distance between these 2 points. Okay, so that's how you just define this function. And it's not obvious from the construction that, it wasn't difficult to define the function, but it's not obvious that this function is actually symmetric. So is it true that, if you measure distance from this direction, this way, is it true that the amount of time it takes this growth process here to reach this point, the same as the amount of time it would have taken the growth process starting from here to reach the other point? So it's not obvious that this is symmetric, and it's not obvious either that from the construction that this satisfies the triangle inequality. So these are two things that you have to check, but luckily here we're in good shape. And the reason is that there's this very beautiful argument, which I advertised before, due to Scott, Sam, and Howe, where they constructed a metric on CLE4. And if you were here at the first conference back in January, you remember that Sam gave a very beautiful lecture about how this argument works. And roughly speaking, what it gives to you is it gives you kind of a high-level strategy or set of conditions that you have to check, which will tell you that a family of growth processes like these ones that I drew here are actually giving you a real honest metric space structure. And okay, so what I want to do is just yep.
Can you just repeat the what conditionally independent, what you mean by that here? Because isn't it measurable?
It's going to turn out to be measurable in the end, but you don't know that a priori. So you just sample, yes, you don't know that to begin with, but there is some conditional law for the growth process given both the quantum gravity surface, given the surface and the location of the point. And so you just sample each of the growth processes from its conditional law given the entire surface independently.
Because the coupling you are doing there is the normal coupling between the SL6 and the GFF?
Well, there's the quantum gravity kind of zipper coupling, and then there's the kind of imaginary geometry coupling, and this is the quantum zipper coupling. So these SLEs, back in the construction of QLE, the way that these chunks of SLE are sampled is that these are actually sampled independently of everything else. It's just an SLE6 inside of this region. So the only way that it depends on the underlying surface is for how long you run it, what the time parameterization is. But otherwise, it's just an independent SLE.
There's no way to view because you're only going to look at the outer boundary of the chunks you add.
Right.
So can you just reinterpret this in terms of some sort of SLE third excursions that are, that the outer boundary of the stuff you add would be some sort of SLE third excursion, and that this is conformally invariant in the same way that the same magic happens in the
yes.
The blue mark point will disappear in the end. So in some sense.
Yeah. So you should be able to do this in a variety of different ways. Why SLE6 is really important is that we know that when you do SLE6, we know exactly what the law of these chunks are. It's a certain type of quantum disk. And if you did something else where we did not beforehand know the exact law of the sort of holes that you're forming, then we would be in big trouble. So I'm not sure. I'm not sure if you can replace this, but in principle, it should not matter what you're doing. But our argument is special for SLE6. Okay, so so what we want to do is we want to check that we're actually getting a metric space on this countable dense set of points xn. And so what is the important kind of observation that underlies the argument of Scott, Sam, and Howe? It's the following. So let's just imagine that we have 2 points x and y, and these are in some metric space. I'll call it m comma d. Then what you could imagine doing is that you sample a uniform number between 0 and 1, and then you grow the metric ball starting at x, whose radius is given by the distance between x and y times u. So this is just a metric ball whose radius is uniform in the distance between x and y. Okay, and then what you can imagine doing is you start growing a metric ball from y, and the radius that you grow this metric ball to is just the first one, so that these ball boundaries touch. So just barely kissing like this. And you get this figure 8 structure. And of course, you can write down exactly what S is. S is just given by 1 minus u times the distance between x and y. And since u is uniform between 0 and 1, 1 minus u, which I'm going to call v, is also uniform between 0 and 1. Okay? And so what this means is that you could have drawn this picture in the opposite order, and you would have gotten the same thing in law. So what you could have done is you could have first drawn a metric ball over here, whose radius is uniform between the distance between these 2 points, and then drawn this one until it first hits it, and you would get a figure 8 structure with exactly the same law that you started with. And what they say is that, very roughly speaking, this is the kind of thing that you have to check in order to get the symmetry of the metric and the triangle inequality. And what I want to do now is just kind of briefly explain how this works in our setting. So you should imagine that we have a sphere like this one. This is our Liouville quantum gravity sphere. And we have our 2 marked points. Let's say this is x, and this is y. And eventually, what I want to do is I want to get to this picture here. But what I do to begin with is I first just draw an independent SLE6, which goes from x to y. So I'll call this path eta, and eta is an SLE6 process which was sampled independently of the surface, and it connects x and y. And what do we know? Well, we know that SLE6, whole plane SLE6, is a reversible process, and so this picture here is going to be entirely symmetric. So we know that both the Liouville quantum gravity sphere and the SLE6, you know, they're symmetric under reversing the order in which this is going. So this picture here is symmetric. All right. And so what we want to do is we want to build on the symmetry of this picture in order to see the symmetry in this picture. And what you do is you have to pick, basically what you do is you pick a random time according to some measure. It's basically the natural measure on cut points of an SLE6. And this random time, let's say it occurs here, this is what's going to correspond to, in just a moment, to the meeting point of these two metric balls, where they're exactly kissing. And, okay, so on the SLE6 side, if you imagine picking sort of a typical, you know, local cut point this way, this picture is completely symmetric still, because, you know, sort of the cut points in SLE6 are going to be symmetric in which direction you're going. So this is sort of this is symmetric. And then what you can do is you can imagine taking this piece of SLE6 here. Let me draw it. I'll try blue so that you have this first part of SLE6. So what you do is you take it and you imagine erasing it, and you replace it by what you would have gotten if you had performed the tip re-randomization procedure to it. And what you get is a chunk of QLE that looks something like this. So you tip re-randomize, and you get a QLE which has holes which look exactly like the SLE6 holes. And then you do the same thing to this chunk of SLE6. So you erase it, and you perform the tip re-randomization procedure. And when you do that, you get another chunk of QLE, but starting from Y up until it meets the first QLE. And because you started off with a picture which is completely symmetric by the reversibility of SLE6 and the symmetry of these quantum spheres, once you apply tip re-randomization and take a limit, you get a picture which is also symmetric. Okay, so you cannot tell whether or not you know, you kind of grew this metric ball first and the second one until it hit it, or you grew this one first and the second one until you hit it. And so very roughly speaking, you're in a position where you can apply this argument, again due to Scott, Sam, and Howe, to tell you that you really do get an honest metric space structure which is symmetric and satisfies the triangle inequality. All right, so that's the construction of the metric. At this point, you know, you don't quite have that it is the Brownian map yet. Yep.
So what is special about kappa equals 8/3 so far in what you've said?
Oh, the thing which is special is that in the construction of QLE, sort of the natural thing to do where you kind of grow the process involves picking points from the boundary measure. And for other values of kappa, the kind of natural measure that you'd be picking points from in order to grow the process would not be the boundary measure. So it would be a different type of measure. So you wouldn't get something which is going to correspond to first passage percolation for other values of kappa. You get some other growth process.
No, but I'm wondering why the argument that you give for why this defines a metric structure, where did you use that it was...
Where did it use? Yeah, so the reason is that it has to do with the fact that the following thing. So let's say you have your first QLE like this, or this could be a chunk of SLE6, and then you start running your other SLE6 up here. And then you ask yourself, what is the law of the point where you first hit here? And it's very important in this construction that this point is actually uniform from the boundary measure. And for other values of kappa, you won't get that. So this is one of the places where kappa equal to 6 is very important in the construction. Okay, so this is that's how you construct the metric. So at this point, again, you don't see the full Brownian map yet, but you start to see some of the Brownian map structure emerging. For example, we know that the boundary length process for QLE, so kind of how the boundary length is evolving as you grow your metric ball, evolves in the same way as it does in the Brownian map, so it's one of these continuous state branching processes. And we also know that the sort of locations of the bubbles that you see as you grow your as you grow your metric ball, occasionally you cut off bubbles, and kind of the locations where these bubbles appear, we also know they're going to be uniformly at random from the boundary measure. And finally, you know that the profile of distances from a uniformly chosen point are going to be the same as they are in the Brownian map. And so how do you finish it off? Yep.
I want to delay you, but so just I mean the SLE6, then you have your cut points, or you have these jumps which correspond to the sort of beats type.
Right.
And so do they have anything to do with the sort of metric you get in the end? I mean, are these bubbles in some sense that you're saying they're exactly the sort of Poisson point process?
Yeah, exactly. It's exactly the law of the bubbles that you cut off here is exactly the same Poisson point process of bubbles that you get when you run an SLE6 exploration, just like it is in the case of a random planar map. Okay, right, so at this point, what you have is you've defined a metric space, but it's only defined on this countable dense set of points, and the first step is to show that this metric space structure actually extends to something which is homomorphic to the sphere and has geodesics. And what you have to do here is you just have to prove some estimates for the size and the shape of these QLE processes, and these are sort of like Gaussian free field thick points type of estimates. And then you can show that these things, these metric balls, they can't be too big and they can't be too small, and you can get this Holder property from that. And then you have to argue somehow that the resulting metric space structure satisfies the axiomatic characterization of the Brownian map. And kind of the way that this goes is that in the QLE setting, you're actually in much better shape than the original statement of the theorem that I gave was, because you can really see the structure of the geodesic tree is very, very closely related to the Brownian map structure. This is a calculation that one has to do. And then finally, there's a last argument which tells you that the metric space structure for the Brownian map actually determines the Liouville quantum gravity surface. And this argument is actually based on an idea which appeared in our work with Bertrand du Plantier on the mating of trees, where we showed that another type of scaling limit for random planar maps determines the Liouville quantum gravity structure. And there's some way to get this type of argument to work here too. And you see that the conformal structure of the Brownian map is a deterministic function of its metric space structure, metric measure space structure. And let me just end with some further questions. So one kind of big mystery is, we know how to take the geodesics on the Brownian map and embed them using QLE, and you get some kind of random continuous curve. But we don't know how to describe what the law of these geodesics, as curves, how do they behave? In particular, we don't even know what their dimension is, and as far as I understand it, there actually isn't even a physics prediction for what the dimension of these geodesics is. And then finally, the even bigger mystery is what happens when gamma is not equal to the square root of 8/3. So here, we lose one of the big crutches that we had in this work, and that's that we don't even have an explicit description of what this metric space structure is. So we don't know kind of what the analog of the Brownian map would even be in this case. And an even more basic question, which has been the subject of a lot of controversy, is what is even the correct dimension of the metric space which might correspond to other values of gamma. So there's this very precise prediction from the physics literature by Wadabiki, but nobody knows mathematically whether or not this prediction is right or wrong. This would be another great thing if one could work that out. And I'll stop there.
Okay, so thank you for a very nice talk. Any questions?
So just from the middle onward, you were working entirely just with the Brownian map and Liouville, but you were no longer working with any discrete.
There's no discrete approximations. There's no conformal embedding.
So just want to try to, I mean, the way the growth process for kappa equal 4, I mean, sort of the way we understood it was always to try to say, well, you have this bubble measure that is completely conform invariant and that has the right scaling feature that makes it possible. So now, is my understanding correctly that in some sense here you have in the square root of a third Liouville quantum gravity setting, that sort of, because of this, have another dimension, the boundary things scale in a different way. The one that will give rise to the actual scale invariant coupling with the Liouville quantum gravity will be the sort of SLE a third bubble or the envelope of this SLE a third sixth chunk that you add. Could that make any sense? Or this sort of
I mean, kind of the difficult thing is that you have to get somehow the time parameterization. I have something I have to think about more. Maybe a question to think about. Yeah.
So can you just try to summarize what is the difficulty in trying to say something about the discrete approximation? So why doesn't it follow that the uniformization of planar maps converge to?
So my understanding is that, so I'm actually not an expert on the discrete approach. My understanding is that one of the biggest difficulties to getting, say, the circle packing argument to work, to show that you even get something which converges, is that it's not even known whether or not, say the largest circle even decreases in size to 0 when you set a number of bases to infinity, because you don't have good enough control on things like that. So even just sort of these sort of basic things are a significant barrier. But probably either Stefan Rode or Nicola would be in a better position to discuss these issues further.
On your previous slide, or
Yeah.
You said there was some controversy about what the dimensions should be.
Right.
There were some predictions by physicists. Can you say a little bit about what kind of conjectures are there?
Well, so there's a very precise formula which was derived by this physicist Wadowicki about 20 years ago, and what it says is that the dimension, looks something like this. So this is this is gamma squared, and if at the gamma squared equals 8/3 line, this curve exactly passes through 4. So this is what the conjectured dimension is. And as gamma squared goes up to 4, which is sort of the critical value, this value increases all the way up to about 4.7, and here it's about 3.56. So there's this formula, and you get a curve which looks like this. And people have done numerical simulations, because you can simulate random planar maps, and there are ways of guessing what the dimension is. And people have gotten answers which are kind of all over the place. So it's been very hard to confirm, even numerically, whether or not this should match up. And so I'm not an expert on Wadowicki's work, but my assumption is that sort of underlying it, he's assuming that you have something like the KPZ relation working for giving you this dimension, and it's not really clear whether or not that assumption should even hold. Right. So it's just I've actually done simulations myself, and I don't claim to be a very good person at numerical analysis, but when I did it, I got something which was kind of close to this, but the error bars are just so big that it's hard to tell whether or not this is conclusive evidence either way. So I don't.
Other questions? All right, we have tea until 3:30, and let's thank Jason for a very nice talk.